This video is one of a series of videos I've made for students who are learning physics to prepare to enter a diagnostic medical sonography program. To find other related videos, please see my playlist, Physics for Diagnostic Medical Sonography Students. In this video, we're going to cover the concept of pressure and also look at fluid statics. The word static simply means stationary. So here we'll be talking about fluids that are not moving. In our next video, we'll talk about fluid dynamics, or moving fluids. The first thing we want to do is define pressure. Pressure is defined as the force per area. And we've got a little diagram here that shows a force exerted on a certain area. Pressure is simply the force divided by the area. Pressure is a scalar, it's not a vector, and I'll talk more about that in a moment. But let's look at the units of pressure. We can see that force has units of newtons, and area has units of meters squared, and that would show us that the units would be newtons per meter squared. We define the SI unit for pressure to be the Pascal. So 1 Pascal is 1 Newton per meter squared. Let's look at a few examples of pressure just to kind of get the idea of this. Imagine that we compare standing on 2 feet versus on 1 foot. So if you start out on 2 feet, you probably don't feel very much pressure on your feet because you're so used to that. But now balance on just 1 foot. Can you feel the fact that all of a sudden now there's just more force per area on your foot? So there's a higher pressure. So that gives you a sense that since pressure is force per area, you'll notice that if we lower the area, that's going to raise the pressure. Let's actually do a numerical example just to illustrate this. So let's calculate the pressure in both of those cases. We're going to assume that our person has a mass of 80 kilograms. That's about 176 pounds. And each foot has an area of 0.025 meters squared. So the first thing we have to do is figure out, well, what is the force acting on either 1 foot or both feet as you're standing there? And of course, that's just your weight. So the force down on your feet, that's just your weight. And we know how to calculate the weight. Weight, remember, is just equal to the mass of the object times the acceleration due to gravity. And so in this case, we have 80 kilograms times the acceleration due to gravity of 9.8 meters per second squared. And if you calculate that, you should get 784. And remember that weight is a force, so it has units of newtons. So 784 newtons. So now let's look at the pressure in the two different scenarios. If we look at standing on 2 feet, to calculate the pressure, we would simply take the force and divide that force by the area. So in this case, we've calculated the force as 784 newtons. We know that the pressure, or we know that the area of each foot is 0.025, but we've got 2 feet now, so that's 0.025 plus 0.025 in the denominator. If you calculate that and change it to scientific notation, you should find that the pressure is 1.57 times 10 to the fourth, and that would be pascals because we're dividing newtons by meters squared. Well, we know that the pressure should be higher on 1 foot. Let's calculate that. If you're standing on just 1 foot, then we can see that what changes is the area. In other words, you still have to support all of your weight, so we've got 784 newtons, but now we're only dividing by the area of 1 foot, so 0.025. And when you calculate that, you're going to find that the pressure you get is 3.14 times 10 to the fourth pascals. Now, you really could have seen that without doing the calculation that way. In other words, if we've cut the area in half, then the pressure would have to be doubled. So you can feel that. When you stand on one foot, you can feel that there's much more pressure on that one foot than there was when you got to spread your weight over both feet. Let's look at another example that is maybe a little bit more dramatic. And that is, imagine applying the same pressure on someone's arm, either using a finger or using a needle. And so I've given you some numbers here to work with. A fingertip has an area of about 0.00015 meters squared, whereas of course the tip of a needle has a very small area. So notice it's 2.6 times 10 to the negative ninth meters squared. And what we want to do now is calculate what is the pressure from your finger, or from a finger on an arm, versus a needle on an arm, where they're both exerting the same force. So you might want to pause the video and just calculate both of these yourself. Okay, so let's see how you did. We know again that pressure is force per area. And so in the case of the finger pushing on the arm, we've got a force of 2 newtons, but now we're spreading that force out over an area of 0.00015. By the way, just to make the difference more obvious, let's put that in scientific notation first. So you'll notice that's 1, 2, 3, 4, or 1.5 times 10 to the negative fourth meters squared. That's quite different than 2.6 times 10 to the negative ninth meters squared. You'll notice 5 decimal places different. Okay, so let me write that down here. We have 1.5 times 10 to the negative 4. And if you do that on your calculator, you should get a pressure of 1.3 times 10 to the fourth. And again, since that's newtons divided by meters squared, that's a pascal. So now let's do the same thing for the needle. We're going to expect to get a much higher pressure because the area is so much smaller. So if we take the force divided by the area, again, we're still exerting that force of 2 newtons, but now we're doing it over a very small area. That's just the little tip of the needle. And that's 2.6 times 10 to the negative ninth. If you do that on your calculator, you should get an answer of 7.7 times 10 to the eighth pascals. So you'll notice much, much higher pressure. And of course, that's why your finger doesn't go through the arm, but the needle does. It turns out that there are some other common units for pressure. One of them is called an atmosphere, or ATM. And we're going to talk more about that in a minute, because that is the pressure due to the air at sea level. So we'll come back to that concept. But for right now, think of it as just a different unit, where 1 ATM, 1 atmosphere, is equal to 1.01 times 10 to the fifth pascals. Another unit of pressure that you're probably familiar with is pounds per square inch. So if you've ever filled up the tires of your car or your bicycle, you know that that is usually measured in PSI, pounds per square inch, where 1 pound per square inch is equal to 6,890 pascals. So just different units to measure pressure with. Let's do a unit conversion, just because it's always good to keep practicing this type of question. It says we found the pressure of a needle was 7.7 times 10 to the eighth pascals. What is the pressure in PSI and ATM? So let's start out by figuring out the pressure in pounds per square inch. We've got our pressure is equal to 7.7 times 10 to the 8th pascals. And we know that when we want to convert, we're going to use parentheses here and put in our conversion factor. And since we have Pascal up here in the numerator, we want it to be in the denominator. So I've got to put that 6890 Pascal down below. And then up above, I'm going to put 1 psi. And so in this case, we can see that we've set this up right because pascals will cancel with pascals. And mathematically, we're just dividing by that 6,890. And what we get is a final answer of 1.1 times 10 to the 5th psi. Let's also convert it now into atmospheres. So the pressure again was 7.7 times 10 to the 8th Pascal. And now the conversion factor we have to use is that 1 atm, 1 atmosphere, is equal to 1.01 times 10 to the 5th Pascal. So again, you can see that we've got this set up right because Pascal will cancel with pascals, and we're going to be left with atmospheres, or atm. When you do that math, you should get 7.6 times 10 to the 3rd atmospheres. Okay, so most of the time we'll use pascals for pressure, but those other units are commonly found, and so it's good to be comfortable converting in and out of those units. Now we want to shift our focus to looking specifically at pressure in fluids. So let's remember what a fluid is. When we use the word fluids in physics, we mean both liquids and gases. So probably in everyday life when you hear fluid, you think liquid, but fluid actually means both liquids and gases. And a fluid is simply a substance that can flow. Now what do we mean by that? What we mean is if you take a container and you fill it with a liquid, we know what will happen. The liquid will simply settle down into the container and take the shape of the container. So if the shape of the container was something like this, like a flask, again, if we start putting water in that, it simply fills in the bottom of the container. Now, a gas is going to flow into a container as well, but because the molecules in a gas have more energy and are basically free to move around, they will fill up the entire volume of the container, as is shown in that diagram. So now let's look at pressure in a fluid. In a fluid, the pressure acts equally in all directions at any given depth. So remember how we said that pressure is not a vector, it's a scalar. This is why we say it, because it doesn't act in a particular direction, it acts equally in all directions. The other thing, or one of the other important things about a fluid, is that when it comes up against a surface, it exerts a force perpendicular to the surface. So in other words, the water in this beaker would be exerting a force outward on the side of the beaker, but it would be exerting a force down on the bottom of the beaker. The other thing that we learn, and this is the most important, is that the pressure increases with depth. We'll talk about this more in a little bit, but if you've ever gone diving in a pool or in a pond or the ocean, you feel that the deeper down you go, the more pressure you feel, especially in your eardrums. And that's because the deeper you go, the higher the pressure is. So as we go lower in this liquid, the pressure is going to increase with depth. Now, why does the pressure increase with depth? Well, what you want to think about is if we're talking about a point right here in the fluid, there's all this fluid up above that, and it's essentially the weight of the fluid above the point that you're interested in that's responsible for the pressure. Um, so let me just write that down, that the pressure is due to the weight of the fluid above. And this is something that, if you ever played with kids, this is something I used to do with my kids. You're lying there on the ground, and then one of your kids comes and lies on top of you, and you feel a lot of pressure, right? You feel that pressure down. Well, why do you feel pressure? Because their weight is lying on you. And so in the same way, if you're down here in the fluid, all of this fluid above, the weight of that is what's creating that higher pressure as you go down into the fluid. So let's look at the formula that is used to describe this. The formula is that the pressure at a depth h compared with the pressure at the surface is simply equal to the density of the fluid times the acceleration due to gravity times the height from the top of the fluid. So in other words, if I want to know what is the pressure at some depth h from the top, this is the formula that allows me to calculate it. Now, you'll notice that I tell you here that it's the pressure compared with the pressure at the surface. We'll come back to that idea in a minute. But in other words, the pressure down here at some height h relative to the pressure at the surface is just given by that formula. One other thing I want to just comment on with this formula. In many books, the way you'll see this written is P is equal to rho GH. So that is the Greek letter rho, and it kind of looks like a cursive P. Looks like that. So many books use that Greek letter rho instead of capital D for density. But since I've used capital D in my earlier videos in this course, I'm just going to stick with that. Okay? It's just a different notation, but obviously the same formula. Before we try that out numerically, let's look at this question. If we have a container holding water and we poke holes in the side, from which hole will the water come out the fastest? So let's say that I poke a hole right here in the container, right here in the container, and right here in the container. In which hole will the water come out fastest? So think about that for a minute. See if you can figure it out. Well, here's what we know. We know that the pressure increases with depth. And we also know, since pressure is force over area, at a given depth in the fluid, the greater the pressure means the greater the force that's exerted on the walls of the container. So up here at the top, the pressure is low. And so that water would not be forced out of the hole very fast. It would just kind of come down something like this. As we go down, we go from low pressure to high pressure. And so the next hole, the water would be forced out a little bit faster. So it might look something like that. And then at the bottom of the container, that water would be forced out very fast and would go something like that. So just another example of the fact that the pressure increases as we go down in a fluid. Let's do a numerical example now. What is the pressure at the bottom of a swimming pool compared with at the surface? The pool is 3.5 meters deep and the density of water is 1,000 kilograms per meter cubed. So here's an example where we're using our formula. The pressure is just equal to the density times the acceleration due to gravity times the depth that we've gone down. And again, this formula is giving us the pressure at that depth relative to the pressure at the surface. So here's my swimming pool, and the water level is up here, and I'm going down to the bottom of the pool where the depth is 3.5 meters. So we can just plug our values into the formula. The density is 1,000 kilograms per meter cubed. G is 9.8, and the height here is 3.5 meters. And this is going to give us our pressure in pascals. So if we calculate it, if you plug it into your calculator, you should get 34,300. And let's put that in scientific notation. So 1, 2, 3, 4, 3.43 times 10 to the fourth pascals. So that would be the pressure at the bottom of the pool relative to the top of the pool. Now, one question that's kind of interesting is, does the size of the pool matter? In other words, maybe I have a very small pool, or maybe I have a very large pool. But you'll notice that if the depth of the pools is the same, the pressure at the bottom is the same. In other words, there's nothing in this formula related to the size of the pool. The only thing that matters is the depth. And so whether it's a big pool or small pool, the only thing that affects the pressure is how deep are we from the surface of the pool. So I'll put a big no. The size of the pool doesn't matter. We now want to talk about atmospheric pressure. We're all surrounded by air, and we don't perceive this because we live our whole lives in the air, but there's actually quite a bit of pressure on us from all sides due to the atmosphere. And that's what we call atmospheric pressure. Now, you remember when we talked about where pressure comes from in a liquid, which of course is a fluid, we said it's the weight of the fluid above that creates that pressure. And it's the exact same thing here for the atmosphere. Picture the column of air all the way up to the top of the atmosphere that is above you just as you're standing here. Well, the weight of all of that air above you, that weight is what's responsible for the atmospheric pressure, the pressure that our bodies experience. Okay, so it's the weight of that column. So the weight of that column of air. Now, one of the things that's kind of interesting about the atmosphere, I don't know how you picture it, but in other words, if I said, here's the Earth, draw how big the atmosphere is, how would you draw it? Would you say the atmosphere is something like that? Well, it turns out that if I draw the Earth to this scale, the atmosphere, the thickness of the atmosphere is less than the thickness of that line. So the atmosphere, it looks very big from our perspective, but if we draw the Earth at a scale like this, the atmosphere is very, very thin. So literally it's like less than the thickness of that line. And you can kind of get a sense of that with this diagram, that the atmosphere is really just, this little bit above the Earth. So what is the atmospheric pressure at the surface of the Earth? It's 1 atm. So 1 atmosphere is the pressure at sea level. Now, you can imagine if you go up to a tall mountain, so let's say instead of being here at sea level, you're now way up here on the top of Mount Everest. there's not as much air, there's not as much atmosphere above you as there is if you're at sea level. And so the pressure goes down as you go up, just like if you go up higher in a swimming pool, there's less pressure on you. So let's look at now the concept of total pressure. Again, you'll notice that when we've been doing these examples of the pressure in water, I've been careful to say it's the difference between the pressure at the surface and the pressure at the depth h in the liquid. So the formula that we have, P is equal to dgh, that's the difference in pressure between the surface and where you are in the water. But it turns out that there's also the atmospheric pressure that's at the surface of the water as well as within the water. And so if we want the total pressure, we have to do something different. By the way, this is often called the gauge pressure. And I'll talk about a little bit more about why we call this the gauge pressure. But let's look at this question. So it says, what is the total pressure at the bottom of the 3.5 meter deep pool? Well, we figured out that the gauge pressure previously was 3.43 times 10 to the fourth pascals. So that's what we determined before. But that's actually not the total pressure at that point, because the total pressure is the gauge pressure, in other words, the pressure due just to the water, plus the pressure due to the atmosphere. And we know that at sea level, the pressure due to the atmosphere is 1.01 times 10 to the fifth Pascal. And so the total pressure at point 8 would be the gauge pressure, that's the pressure just due to the water, plus the atmospheric pressure. So let's just figure out what that is. That's going to be 3.43 times 10 to the fourth plus 1.01 times 10 to the fifth. And what we get then for the total pressure is 1.35 times 10 to the fifth Pascal. So the one thing you have to be careful of in a problem is, are you being asked for the gauge pressure, or the pressure difference between the surface of the water and the point a distance h down into the water, or are you being asked for the total pressure? By the way, total pressure is also sometimes referred to as absolute pressure. This concept of gauge pressure versus total pressure can be confusing. So let me show you why we call it gauge pressure. The best way to do that is think of when we use a gauge, and something that you've probably done at some point, which is, have you ever checked the tire pressure either in a car or on a bike? Well, you are measuring the gauge pressure when you do that. In other words, the gauge pressure is the difference between the pressure inside the tire versus the pressure outside the tire. Whereas the total pressure would include the additional pressure inside the tire plus the atmospheric pressure. So let's calculate this to make it concrete. Our question says the gauge pressure in a tire is 35 psi. What is the pressure in pascals, and what is the total pressure inside the tire in pascals? So again, the gauge pressure is given. The only issue here is it's given in pounds per square inch. And we want to convert that to Pascal. So in this case, we now see we need the PSI on the bottom and Pascal on the top. So the PSI cancels with PSI. And if you do that, you'll find that the gauge pressure inside the tire is 2.41 times 10 to the 5th Pascal. So that's our gauge pressure. But that's just the difference in pressure between outside the tire and inside the tire. That's not the total pressure, because the total pressure is the gauge pressure plus the atmospheric pressure. And again, we'll assume we're at sea level. So to figure this out, we're just going to take that 2.41 times 10 to the 5th pascals for the gauge pressure. And then we've got to add the fact that the atmosphere adds an additional 1.01 times 10 to the 5th pascals. And so the total pressure inside the tire, or again what we refer to as the absolute pressure. So again, I'll just mention that you'll hear it talked about as total or absolute pressure. What we would get is just adding those two, we would get 3.42 times 10 to the 5th Pascal. And so that's our answer. Here's a conceptual question to look at. In fact, let me show you two. The first question is, in which tube is the pressure the highest at the height shown? So in other words, where the dotted line is here. And then how about in this diagram? In which of those tubes is the pressure the highest at that dotted line? So you might want to pause the video and think about that for a moment. Okay, well, let's look at this together. So what did you say for the first one? Hopefully what you said is the pressure is the same at that depth in all of the containers. So why is that? Well, remember that what we've said is the only thing that matters is the depth in the fluid. And you'll notice that in each of these cases, that depth down to the dotted line is the same. We saw that when we talked about the swimming pool, the shape of the swimming pool doesn't matter. The only thing that matters is the depth of the pool. And so this is really just another example of that. The shape of the container doesn't matter. Simply the depth down from the surface is what is going to determine the pressure at that point. So the pressure in all of those containers would be the same at that dotted line. But if we now look at the next one, which of those would have the highest pressure at the dotted line? Hopefully you answered this one, and that's simply because the depth is the greatest in that case. So because the water level is highest there, at the dotted line we're down the farthest in the water, and therefore it would be the highest pressure. And I'll just write highest pressure. And again, remember where that pressure comes from. It just comes from the weight of the water above, and we can say there's more water above. And that's why the pressure is higher. Let's look at one other conceptual example that is, I think, pretty interesting. And that is, why do your ears hurt or pop in an airplane or when diving underwater? So if we look at the anatomy of the ear, this is the outer ear here. So that's just your ear canal. the place you're not supposed to stick Q-tips, but everybody does. So you can you can certainly see that outer part of your ear. And if you've ever had a chance to look in someone's ear with the tools doctors use, an otoscope, you can actually pretty easily see your eardrum. So your eardrum is this very thin flap of skin right there that completely seals your outer ear from your inner ear. The fact that you've got the eardrum here means that air cannot move between your outer ear and the inner part of the ear. So what happens when you either go up in an airplane or go down underwater? Well, when you go up in an airplane, the air pressure is becoming less. In that case, you're going to have a higher pressure in here than out here, and that's going to make your ears hurt. When you go underwater, the opposite happens. The water underwater, the pressure is going to be higher here than it is in here. And so one of the cool things about human anatomy is that there is a way to equalize the pressure. Okay? So again, that's the eardrum here. That's what blocks the inner part from the outer part. And if there were no way in here, then whenever the pressure got higher or lower out here, it would make your ear hurt. But we have these tubes called eustachian tubes, and I'll just write that here. So this is your eustachian tube. And what the eustachian tube does is it's a thin tube that connects from that inner part of your ear in sort of behind your nose, in your throat area. And you've probably noticed, if you've ever had a chance to fly in an airplane, or if you've ever done some diving where you have to learn how to equalize the pressure in your ears, you can do things like sort of try to blow your nose but not really blow it, or you can try swallowing. What you're doing is you're letting air come either in or out your eustachian tube to that inner part of your ear, so that the inner pressure inside your ear is balanced with the outside pressure. And so if you're ever going in an airplane, as you're going up, one of the things you can do is chew gum. It helps you swallow. It kind of opens up that tube momentarily, and you can keep doing that to balance the pressure as the plane is going up. And then once you're up at a constant level, you don't have to do anything. But then as you're coming back down, you have to do it as well, because as you're coming back down, the pressure is increasing on your outer ear, and once again you have to balance that pressure. Okay, in our next video we're going to look at fluids when they are moving.